While it's running, I want to share this notebook uh, about diffusion. It's the video. The the notebook that David created for a demonstration of diffusion models, and it has also visualization how the images um, uh, remove noise from and I didn't know that you can do this on TensorBoard. Yes. Yeah. So yeah, you can play with this notebook when you have time. And also I uploaded the conditional diffusion models where the condition is the half of the image and they reconstruct the second half of the image on my courses. So let's look at the version. Uh, what should I do? Print? No. Oh, it's marked down, maybe.
Yep.
Oh, so it was
So it was updated
oh, it was older?
because it was 4.49 when I did the homework.
Ah,
So they must have just updated it within the last, couple weeks.
okay, yeah. Because I ran notebook and it was broken, and so if you want Justin to to get the points, you can maybe run on this if you want.
Do you want us to rerun and submit it?
If you want to,
Okay.
but I think you have extra points from
You're
previous
right.
homeworks. Okay, so let's finish our yeah discussion of the um, s- speech understanding. Okay, so last time, yeah, we stopped on the this image, how we can uh, detect characters from the spectrogram. But actually, we can also detect phonemes instead of characters, and also we could detect subwords also. Um, so the model returns the probability of every character from our dictionary, and then it predicts the character. But um, the problem is that some frames kind of corresponds to the same character, and we have repeated characters. And to fix this problem, uh, we can train our model to return like blank symbol. For example, if it um, doesn't understand maybe what the character was pronounced, or maybe there is a silence. And um, also maybe between repeated characters, there will be a silence. So as the result, we will get a word with these blank symbols, and after that, we will combine repeated characters. So every repeated symbol will be combined into one symbol. And after that, we will remove this blank symbol. So this is the idea. So during training, we have also the words, we have the target. So if we know the target was hello, the prediction from the model of the word hello like this will have a problem, because if we remove the blanket symbol, we will get triple L instead of dot. And such reconstructions we will call non-valid predictions. So we want to work only with valid predictions. And here the so-called CTC loss comes into play. So it's called connectionist temporal classification loss. Well, here's just an example how we can compute the probability of the sequence because we have the probability for logit for every frame. So if we choose, for example, argmax, we will choose the character with highest probability. And then we can calculate the probability of the entire sequence. And yeah, for different sequences, we will have different probabilities. Okay, and this is our loss function. We have prediction y, and we have the true word x. And we want to calculate all valid predictions. Valid predictions for the given word x. The problem with this well, maybe in this case, it's just overall predictions. The problem with this function, if we compute this probability over all possible predictions, it has exponential time complexity if we use all the combinations. So in this CTC loss, in 2015 was proposed to use only valid predictions. So what is this? Well, first of all, the next slide shows how to compute the probability recursively. So for example, we have the prefix AB, then we can calculate the probability of AB and condition that the last symbol was B, or that it's maybe a sequence of 3 tokens, And the last character is this blanket symbol, because after that we will remove this blanket symbol and we will get again AB. And then we compute each of these terms, using the conditional probability. So to get AB, we can get the first symbol A and the last character B times probability that the last character equals to B. Also, we can have the prefix A, the last character, this blanket symbol times probability that there was B in our after this blanket symbol. And also we can have repeated characters, because you remember we could like glue them together. So we could have prefix A, the next character A, and the next character B. If we have the last character epsilon, then there are two options. We have prefix A, next character B, and then epsilon, or we have prefix A and 2 times epsilon, because epsilon will be removed. Well, it's just to give you an idea how we can compute these probabilities, and we, of course, we will use the dynamic programming for that. So we will plot this graph. So, for example, our target word was AB. We will just insert this epsilon, this blanket symbol, in front and in between all the characters in this axis. And these are our predictions. Axes are predictions from the model. They correspond to each frame of the spectrogram, for example. And we want to reconstruct only valid predictions. So you can see that from nodes, there are only 2 or 3 errors from every node. So, for example, after epsilon, like blanket symbol, we can't get B. So there's no error to B, because the word begins with A. That's why we have only errors to epsilon or to A. From A, we can get B. We can get B. Also, we will get epsilon, and we can get again A, because repeated characters will be glued together. But we can't get A, epsilon, A, for example. So we can get A, epsilon, and then again A. So that's why there is no error from this node to A. From this node, we can get only B or epsilon. So this is how we can limit ourselves just by valid reconstructions instead of all possible combinations. And yeah, this is the illustration how we can compute. And this is called CTC loss. And then we can apply gradient descent to update these probabilities. So it produces the alignment between our audio, and our target words. And also because we have several different possible paths, different possible outcomes. Um, well, this is the problem if we take argmax. So typically, yeah, we don't take argmax, we just apply beam search. So yeah, so because we have probability distribution for every frame, we are not limited just taking the highest probability token. And if we choose the size of beam search, we can actually consider different possible reconstructions of the symbols. And here, language models help with reconstruction because let's see if there are examples. But this is during inference. So beam search we apply during inference, not for training. For training, we have all possible paths in our CTC loss. But for inference, we apply this beam search. Let's see if there is a result. No, I don't see the result. But, or maybe it will be later. Because if we have several outcomes from our speech recognition model, we can choose the most probable word using language model, because language model, you remember hello or hell. So, for example, our model won't understand the context because hello world or hell world, it will be the same. But if we apply beam search, it will produce different sequences, and maybe between these sequences we will have hello world and instead of hell. And then we can apply language model on these sequences after beam search. And language model actually will return also probability of our sequence, and then we can choose the highest, the sequence with highest probability, but from language model. So these data sets like LibreSpeech in their work page, they have pre-trained language models. Very simple, just n-gramly, not without any neural network. Very simple language models, then n-gram neural that we built maybe on the first or second week of our class. And applying language models after this beam search improves quality of the speech understanding. Here's the model. The model, which is called deep speech, the first deep learning model for speech recognition. And it was trained on this connectionist temporal classification loss. The input features raw spectrograms, and here we just had recurrent neural networks. And this is 2015. Yeah, you can see that the quality word error rate on the clean data set was pretty reasonable. Yeah, but still not it didn't beat the human performance on the other parts. Other parts, you remember, it's the part where of the speech where the speech recognition model failed. Okay, so this is the first model. Now, instead of the recurrent neural networks, of course, we can use transformers. And people try to apply transformers, but it appeared that if you remember, audio, if we work on waveforms, is represented by very, very long sequence, 16K for 1 second, for example. And then we kind of to shrink this data, we apply convolution layers, because if we apply convolution layer, it will, and especially with stride, when we apply this convolution layer, not with shift by 1, but for example, we shift by 300. So when we apply convolution, 1D convolution layers, we will reduce the dimension of our audio signal. And people notice that instead of using just the transformer, which we used in language models in NLP, for speech, it's a good idea to add convolutions. And they call this conformer instead of transformer. So the only difference with transformer model is that after this self-attention, we have also convolution layers. And in speech, so typically conformers are used, but these are the same transformers, but with convolution layers. And let's see. I don't know, maybe it's interesting. These are technical details, but did you hear about depth-wise convolution? So it's also used in image processing. Again, it's technical details, but I think it's good to know because it's used in many models to reduce the parameters. I don't know, David, can you explain or?
So with the regular convolution, you have
So this is the regular convolution when we have filter which has this last side as the number of channels of our data.
yes, so each filter is applied to each channel individually, and then so
In depth-wise. Or
in standard convolution, each one's applied to each other channel, but in depth-wise, they're separated. So each filter is only applied to one channel.
yes.
Standard.
Yes, in depth-wise convolution, we apply a filter, but channel-wise. But you remember from one filter, we should get the one-dimensional feature map. So how to get one-dimensional feature map from this filter where filter is applied kind of for every channel. So what is the last component?
pointwise convolution.
Yeah, so
Oh,
to get just one dimensional output.
yeah, that's like a mixing channel.
Yes, so in depth-wise convolution, we apply one by one convolution to this channel-wise convolution filters. So it will kind of convolve along channel dimension. And after that, we will get one-dimensional feature map. But let's think about a number of parameters. Here we had in this example, we have 5 by 5 by 3, which is 75. 75 by 3. 75 parameters. And here we have 5 by 5 by 3, also 75, plus 3. But yeah, for one layer, it doesn't make sense. But if I want to get the output shape, for example, 256 channels, then we will need to apply 256 filters of this shape. So it will be 256 filters times 75. Or I can write just 5 by 5 by 3. If we want to get 256 channels with depth-wise convolution, we will apply our channel-wise filter. It will be 5 by 5 by 3. So then we apply this filter. It will be plus 3, plus 3. So that's how we'll get to 56 channels.
There's do 256 by 1 by 3. Because that's your mixing channel there. And you need 256 then.
Oh, so I don't.
You don't need the plus 3.
Yes.
That is just showing the pointwise convolution is. Then you can do plus 256 times 1 times 1 times 3.
Oh, yeah, because I will think you did. Correct. Because yeah, so plus 256 times 3. So you can see that we will have much less parameters. Of course, they're not equivalent, these transforms, but in practice, depth-wise convolution actually performs better than full convolution. It came from images, but people used also this in audio processing. Okay, so as I mentioned, we can use also BPE tokenizer. Instead of predicting characters, we can predict tokens. Yeah, and this is how language model can be used for prediction. Of course, I told you about the simplest approach, just post-processing, but in practice, they've used these language models also inside architecture. Okay, now let's talk about approach without spectrograms, how we can learn text directly from audio, like in Llama 3 models. And this is called self-supervised learning. Like word2vec, you remember, it's also a self-supervised learning. We learned word embeddings from texts. Here we will learn embeddings for audio from just raw audio recordings. Like in images, also visual transformer learned embeddings for images. Where is it? Animation slideshow. And we'll skip this different paradigms like supervised, unsupervised, also supervised learning. Okay, so as you remember, we have three types of models: encoder only, encoder decoder, and decoder only. And as you can see from the number of models, decoder only are more popular, like GPT-like models. And so in speech, there are also different models, and encoder, decoder, and encoder only. So now we will talk about encoder only, like BERT. Our goal is to represent raw audio with vector embeddings instead of spectrogram. But the problem is we don't have a vocabulary. Like in language, we have a vocabulary, we have tokens. So the first approach here, okay, let's look first at the taxonomy of these models. Yeah. So the first word, it's a word speech to vec, VAV to vec. So we will talk about VAV to vec, a model about where is Hubert? Hubert and VAV with LM and BERT RQ models. So you can see how many different models try to implement this idea sound to vectors. So the first approach was VAV to vec, and they applied to raw audio convolution layer just to reduce the number of data. So this is the called feature extractor. So there is a convolution layer with stride, if I remember correctly, of 320. So instead of 16,000 points for 1 second, we will have I don't remember exactly, but maybe 300 tokens instead of 16K. So this is the first layer, feature extractor, and then we apply actually they apply several convolution layers, and then we can mask some tokens like we did in BERT model, and then we want to predict the masked tokens. But again, the problem is what is the target? We don't have tokens for sound. And in this first approach, they created so-called code book kind of in VQ VAE, and trained this code book together with this model. There was a lot. It's not used anymore, so I will kind of go fast through this model. Otherwise, it's a little bit hard to understand how we take the dot products from the token with every element in code book, and then we create a vector. And then we train this similarity function. So we want to make the vector after this code book as similar as possible to the output from this transformer model. And there is a problem that model will learn, for example, the constant embedding for the silence, because we have more silence typically in audio tokens, and to kind of force the model learn other embeddings, they used negative entropy, because if we want to increase entropy, it's the same as to decrease negative entropy. So they had negative entropy, and entropy, like larger entropy, creates more diversity in our tokens. So this is the first model. And when this model, well, yeah, there also is discrete, so we should apply Gumbel softmax to get the gradients for discrete distribution. But here are the results. After, you remember in language, when we used word-to-vec model, instead of just one hot encoder embeddings for the words, all other tasks actually worked better. Like we have text classification, for example. So the same idea here. After they trained these embeddings for the audio and applied this embedding for speech recognition task, they got the one-digit word error rate on this other part of Libre speech data set. And there are other comparisons, like also it's interesting, they could train only on 10 minutes of audio. They could train the model only on 10 minutes of audio. So it's also very interesting and gets pretty low word error rate. Then so how to use this embeddings for actually text recognition? They fine-tuned this model on this CTC loss. So they used these embeddings as input and use this dynamic programming to fine-tune these embeddings. And you remember from these predictions, we can get actually the words after adding blanket symbol, after gluing together. So this is how they actually apply this model for text recognition. And the result was really impressive. The second modification from Meta was trained on multi-language data set, but let's move. This is interesting. Let's move to the more recent models, like T5 encoder decoder, when we have input sound and output text, for example, or input sound and output sound. So this plot is interesting because here in this paper they compared the embeddings from raw audio and models that were trained on spectrograms. So what we should actually use? Spectrogram, spectral representation, or raw audio representation? And for example, Google, they work on, so it's kind of historically, if you see any model from Google, it will be on the waveform. If you see any model from Meta, it will be on spectrograms. But which approach is better? So here they compare different models. So we will talk later about Hubert and Bartholomew, but all these models are creating the embeddings, vector embeddings for audio, and they try to calculate the similarity of the spectrogram and the embeddings that were learned with model on different layers. So as you remember, these models, they have first several convolution layers, kind of feature extraction, and then transformer layers. And you can see that around sixth and seventh convolution layer, the similarity with spectrogram is the highest one. And next time, when I will talk about voice conversion and show the results with optimal transport, we actually will use the embeddings for audio from the seventh layer of our model. So just will give you an intuition why we choose the seventh layer, not the 22nd or the 30th from these models. But also this research paper raised the question: if our vector embeddings are very similar to spectrogram on sixth or seventh layer, maybe there is no reason to train our model with 6 layers, but just use spectrogram. And current model actually are all based on spectrograms. So it's interesting how people first kind of decided to work without spectrograms, and after this research, well, for some tasks, these embeddings, for example, for language models, the vector representation is better. Let's see, we have time. Okay, let's move to the yeah, let's skip other models. Okay, Hubert. So the next model, Hubert, it used a little bit different approach for the targets. So they created spectrograms. These are actually a spectrogram of spectrum. They're called MFCC, mean frequency Chebyshev coefficient. So it's a spectrogram of a spectrogram. And because it's a spectrum of a spectrum, it's much shorter. Typically, we can use just like in Mel frequency spectrum, we used 80 beans. In original spectrum, we had thousand of bins. In this MFCC spectrum, we can use typically 11, 13 bins. So they kind of created this MFCC spectrums for their data set, and then clustered these spectrograms into, I don't know what was the number of clusters. I don't know. So for some, maybe 1,000, I don't know, maybe 500, for some clusters. And then they used this labels cluster as the targets for our model. Like in the previous case, they used a code book. In this case, they used the clusters from spectrograms. And you can understand that this model actually forced the embeddings to be similar to spectrogram. Well, there is also one additional trick. They then extracted the 9th layer and continued training on not on the clusters, but all clustered features, but on the features from 9th layer. But these are just details. And yeah, and you can see that even for small amount of training data, 10 minutes or 1 hour, this approach outperforms the previous one. Okay, the next model, more recent, if I'm not mistaken, they just created a fixed code book. So instead of extracting these classes, they just said, okay, let's just use whatever number of the embeddings, k, for example, just k fixed vectors, and train our model to match the features. Or actually, you can see that this model was trained directly on the spectrograms. To match these bins, these frames of spectrum, to match with some code book. And oh, yeah, there is an image. So we use the just fixed embeddings. And this model yeah, provides very, very nice result. I think we don't have time for, let's see, I think we can maybe stop here for today. Yeah, maybe next time I will talk about the language model that uses the audio. Actually, next time I want to talk about options. Maybe I can finish. So this is just idea how you can incorporate voice into large language model. So you create this encoder that converts typically spectrogram or speech into embeddings. Then we use, for example, linear layer just to match the dimensions of tokens, text tokens, and audio tokens. And just pass into our language model. And there are different approaches you can fuse inside the model, or you can just add these tokens and your model will just apply self-attention. So yeah, and here you can see that we have input speech and input speech and output text, and also some prompt in the text. And I think, yeah, there is maybe another model like Llama 3, which can work as speech to speech. So we have speech at the input, then it processes speech as text, and then it returns again speech, kind of speech to text, and then text to speech. So yeah, so today we talked about how we can convert audio into tokens and to text. And next time we will talk about how to convert tokens back to speech. And oh, sorry, next week. Next time I will just use this model to show you the how we can apply this model for voice conversion. But next week we have 2 more days. I will explain how we can convert back spectrogram or embeddings to audio. And I hope on Friday and Monday you will present your projects. I mean, after next week. not this Friday. Yes.
Does that
Just-
mean projects are due on the last Monday of class?
No, but if somebody will be ready, we can maybe just look at the projects. Oh, you can finish until the end of the finals